Hey chemists, welcome to our next lesson in our series all about Le Chatelier's principle and the impact that it has on equilibrium. Yesterday we learned all about Le Chatelier's principle and the impact that changing the concentration has, and today we're going to focus a little bit on changing temperature. So I want to go ahead and start off our first component here with just taking a look at a quick demo video. So let's go ahead and take a look. Okay. So what we're going to do is we're going to take a look at what happens when we add the equilibrium system into both hot or cold water. So notice that as it gets warmer, it is turning to a darker brown color. And as we add it to the cooler temperature, notice that it is turning almost a yellow or a lighter brown color. And what I want to go ahead and do is add this to our notes sheet. So let's go ahead and flip to our notes and put that in our observations for today. Okay, so taking a look here, we're going to add some notes to our sheet. All right. Okay, so when we added this to the cooler temperature, okay, it was brown and we removed heat. And from there, it became a yellow or light brown color. Okay, and then when we had it in a warm environment, it was brown, and we added heat. Okay, we saw a dark brown color. Okay, and I have this set to be extremely thick while I'm writing apparently, so there we go. Let's decrease that a bit. Okay, cool. So what we're going to look at today is how does the addition or the removal of heat impact our equilibrium? Now, the reaction that we saw is a really cool equilibrium reaction between NO2 gas and N2O4 gas. And I've included our equilibrium graph here. And so I want to go ahead and generate a chemical equation for what we saw in the video. Now, notice that we have to go ahead and take a look here at which one of these, in order to determine reactants versus products, which one do we start with some of and which one do we end with? Okay, notice how our concentration is 0 for the NO2, and therefore that is likely going to be our reactant. Okay, and we have N2O4 starting with some, and that's going to be, or I'm sorry, that's going to be our reactant. NO2 is going to be our product. So our reaction here is going to be N2O4 is in equilibrium with 2NO2. And how do we know which substance should be written as the reactant? Again, we know which is the reactant because we know that it starts with some amount of concentration, whereas the NO2 has no starting concentration. So N2O4 has a starting concentration. Okay, which information from the graph indicates that we've reached equilibrium? I threw this in here because it is important to continually review these components. And so how do we know that we've reached that equilibrium point? Okay, if you look, when we've reached equilibrium, our concentration of the NO2 and of the N2O4 goes unchanging. So at equilibrium, the concentrations are, again, keyword here, constant. Okay? Now, how did we stress our system in the video? In what ways were we adding stress? Again, yesterday we talked about concentration. Today we altered the temperature, or we added or removed heat, okay? So our stress was the addition or removal of heat. And so the question then becomes, how do we know which direction equilibrium is going to shift if I add or remove heat? And the answer is that it really depends on whether or not your reaction is endo or exothermic. And so what I want to do is, to that equation that we've generated, I want to go ahead and add the delta H, or our heat, where it is applicable. So taking a look at our equation again, I'm going to go ahead and jot that down here. We have N2O4, again, is in equilibrium with 2NO2. And you may have caught this in the video, but if you didn't, our heat is actually going to belong over here with the N2O4. Okay, so this is our heat. And again, that heat could be written as kilojoules as well, but for now, we'll just leave it as a general heat statement. So is this reaction considered endo or exothermic? And so we have to be careful here, right? We're in equilibrium now. We have both reactions occurring at the same time. So we have to specify the forward or the reverse reaction. Okay, so our forward reaction, okay, in this instance is going to be endothermic. Okay, so our forward reaction is endothermic, right? We add heat energy moving in the forward reaction. Our reverse reaction, on the other hand, is going to be exo. Okay, so the reverse reaction is exothermic. And again, as we move, or as we consider 2NO2 synthesizing to form N2O4, we produce heat, which is why it's exothermic. So before we can move forward and talk about going back to the video and talking about the color shift that we saw, we do need to label these gases by what colors they produce. So it did mention this in the video as well, but again, if you didn't catch it, N2O4, if this were the only gas present, this is a colorless gas, okay? And NO2 is actually a dark brown gas, okay? And so based on these things, based on the color of the gases as heat was added, which way did our equilibrium shift? So let's go back to our notes and take a look here at what color it changed to as we added heat. So when we placed it in the hot environment, meaning that we're adding heat energy to our overall equilibrium system, we noticed that we ended up with a darker brown color, or a dark brown color. So going back and looking here, let's just jot that down. So in heat, it turned dark brown. So as a result of that, which direction did equilibrium shift? Well, looking at our substances here, if we're getting a darker brown color, that must mean that we have an increased amount of NO2 gas, which means that we've shifted to the right, okay? So as heat was added, okay, equilibrium shifted right. Now, what's kind of cool about this is that, take a look, if we treat heat as its own reactant or its own product, we can use the same general rule of Le Chatelier's principle that we used before. So as I add heat, we are going to shift away from that heat, producing an increased amount of NO2 gas. Okay? Now let's use this the other direction. Based on the color of the gases as heat was removed, which direction did the equilibrium shift? Well, thinking about heat being removed here, so in cool, it turned like a light yellow. It turned like a light yellow color. Now, notice that we don't have yellow as an option for our colors, but when we have dark brown and it's shifting away from being dark brown, that must mean it's shifting toward being colorless, okay? Or think of it this way. If I remove heat, like we talked about with concentration, if I remove something, I'm going to shift toward that to try to create more of what I've removed. So if I remove heat, I'm going to shift toward the heat. And as a result, I increase the amount of the colorless gas that I have in my system. So as heat was removed, equilibrium shifted left. Again, to produce more heat because we do require that energy in our system. Now, why do we never just see a colorless gas then? What's our reasoning? Well, remember that we are in an equilibrium system, okay? Our system contains both N2O4 and NO2 at any given moment. We're never going to have zero amounts of either. And so because of that, NO2, which is dark brown, will always exist in our system. So again, when we are in an equilibrium system, okay, so the system is in equilibrium, okay, which means that NO2 will always be present. Okay, we're never going to have no dark color or no brown gas in there because it's always going to be there. All right, excellent. So now that we know about the heat shifts, what general rules can we make here? When we add heat, okay, when we add heat, our general rule is that we are going to shift away from the addition, or shift away from, let's just rather say we shift away from that heat, right? We're going to shift away from the heat. Okay? And again, if this is the case, this means that this is favoring the endothermic reaction. If I add heat, man, our endothermic reaction is going to be going faster, right? If I add heat, that heat's going to get used up. All right, what about then if I remove heat? If I remove heat, then I'm going to shift toward heat. Okay? And again, well, if we're producing more heat, right? If we're trying to produce more, which is favored, our endo or our exothermic reaction? Okay, well, if we're producing heat, that means our exo is favored. Okay, so let's do a quick practice and just see if we can determine, based on what we've learned today, how this is going to impact not only our equilibrium shift, but also how it would impact our concentrations. So taking a look here, we're given our general equation A plus B becomes, or is in equilibrium with C plus D plus heat. So as heat is removed, which way will equilibrium shift? Okay, if heat is removed, that means we need to produce more heat, meaning our forward reaction is favored. Okay, so equilibrium shifts to the right. Okay, how would this impact our concentration of A? Well, again, we're just going to treat heat like it's any reactant or product. Therefore, how is this going to impact the concentration of A? Well, in order to produce more heat, A and B are reacting more frequently, and therefore A is going to decrease, okay? The concentration of A decreases because it is being used to create more heat. Okay? How would this then change the concentration of C? Well, where does C fall? C falls on this side. So not only is heat being produced, but C and D are also being produced. So therefore, the concentration of C is going to increase because it's created as heat is created. All right, everybody, that's all I have for you today. Thank you so much. You guys have a great rest of your day.